So hi, everyone. So I should say this work is mostly done by my PhD student, Vasco Sousa, who wasn't able to make it, and my master's student who did most of the evaluations. So I'm here, but I may not be able to answer all the detailed implementation questions, though. OK. So typically, when we generate domain-specific modeling editors, we usually specify some language definitions, so abstract syntax, meta-model, concrete syntax, grammar, icon definition, things like that. And from that, that's usually enough to generate an environment for the user to define his models and interact with them with a given graphical user interface. And usually that IDE is deployed on or editor is deployed on a specific platform. We're going to focus mostly on graphical domain-specific modeling editors for the rest of the talk. Now, the current practice, so this is an example of a DSL that we built in our tool Atom PM that allows you to define music sheets. And this one here is in Eclipse using Sirius to define a game of life, which is like a cellular automata that has neighboring nodes and things like that. And if I just show you this here, if you would do it in Eclipse, so you have your music DSL expert, right, domain-specific expert. He wants to build his music sheet. There is no way he's going to use your tool if he has to do that, right? There's absolutely no way. He's never going to do that. You see how cumbersome it is to try to use that tool. Same thing for Game of Life. That's extremely simple, of course, but he has to create different cells and then define the neighborhood between the cells. And the black cells are alive, and if they're white, they're dead, et cetera, et cetera. So this is also very inefficient because he has to do a lot of manipulations on that. So instead, what you would want to do is let the user, plug in his MIDI keyboard and just type the things, and then he can just model using his own interactions he's used to. Or here, you can just say, I just need to touch the screen where on the canvas I want to instantiate my dead cells, and they're just going to connect with each other, etc. So to be able to do something like that, we need something related to how the interactions with the editor can be made domain-specific. So to do that, what we propose is to a set of languages that allow you to also not only customize the concepts and the way they are represented, but also the way you interact with the editor so that it can actually generate a fully adapted modeling environment. So here we'll see we have a language to define the interface, the user interface. Also a model to define the interactions that you're allowed to do with that interface, with that editor, and to be platform, to be able to deploy on multiple platforms, some deployment mapping. And from that, that's what we call the operationalization process of this definition. We actually generate a modeling environment with a specific user interface that was defined properly for here. Of course, that integrates concepts from the language. We also define a Statechart controller that will actually control how the behavior of the editor will behave when you're interacting with it. So that's coming from the interactions. And of course, some platform-specific code that is deployed with that. So that's what I'm going to go through. And here's the general process that we follow. So this is your usual stuff, right? Abstract concrete syntax that we will use to generate the graphical user interface and API of the system. We also want some system actions. Here we call them system actions. It's just an abstract way of saying the API specific for if you're deploying on the web, or what kind of actions are allowed to do, your API and things like that, right? So that's what's in this green box. Of course, to be able to do that and to be able to customize it, we need some kind of an interface model that is able to specify how all this is going to look like and not impose always the same user interface. So the interface model looks like this. Here, I'm not showing you the meta models. They're in the papers. So the interface model basically consists of layers, where you have a layer that holds the canvas. As I said, I assume it's graphical modeling that we're doing. So a canvas where you can usually instantiate your language elements. And then you can have additional layers, for example, one for the toolbar, the buttons. You can also have different interaction streams, like an LED light if you want to deploy it on your phone, and when you press run, it's going to turn on the light or something like that, right? So it can be way beyond a screen and a keyboard and a mouse, right? We're just trying to open it. And from there, we generate our initial state chart, our state machine, with one state per layer. Basically, each layer here represents a layer of my user interface, and here I call them layers. They're orthogonal components and states. Basically, the initial states that we have there are the initial configuration that is when you start your editor. So every state that I'm going to have in my state machine are the GUI configuration that are reachable from a sequence of interactions. So given that initial state chart that we generate, it's a super simple transformation, then we apply a set of refinements to be able to basically accept or implement, operationalize the interactions with that. So for that, we need an interaction model that will define how you can transition from one state of the editor to the other state. And that interaction model depends, of course, on the interface, on the language, and also on platform-independent actions, right? I want to say I select this, okay? But what does it mean? On a phone, maybe it means touch, and on some Arduino, it means joystick up, maybe, something like that. So these are platform-independent actions, and then there's, of course, a mapping that defines the mapping between these. So let's look at this refinement, and that's the core of the work here. So the interaction model, we've used what we call rule-based interactions. They come from the user experience in HCI community, where they have things called trigger actions and event condition actions. So here the rules, what do they say? If I look at the first one, here it says, so this is my condition, and this is my effects, and I can have multiple effects happening, and that's my event that happens here. So basically it reads as follows. If I have my focus on the canvas, and I receive the event select, then I will instantiate that game of life cell. If I have a focus on the game of life cell, and I receive a select, then I'm going to delete that cell. If I press the button, then it's going to disable the button and turn on the blue light and call some API function that says run the simulation or something like that. If I receive an internal event that something has finished, right? So if that is asynchronous and something has finished and my button was disabled, then I re-enable it and I turn to green, and then I can toggle the light to be turned off. So given this set of interaction rules, you see they're not semantical rules, they're not operational semantics rules, they're not model transformation rules. They're inspired from them, but it's very much of how I interact with the editor. So the question is, how do I take this set of rules and have some controller that is able to take care of all the possible interactions that can happen? Now, that is a very tricky transformation. We're doing MDE, so we try to actually model it using a model transformation. But the challenge is that any rule here could be applied at any time. When you define a model transformation, you usually have to define a priori a scheduling of the rules. In this case, it's not possible to know in advance what can be applied. So it may be that, for example, rule C is applied, which disables the button and turns the blue light on, but that may enable some rules that were disabled before, right? So you have to be able to reevaluate all the rules all the time and keep track of that. Furthermore, we need a transformation engine that controls how the configuration should be evaluated and combine partial evaluations and not the complete evaluation. So you don't need to match the whole thing, but usually when you do an interaction, it's a very small thing that changed. So you want to optimize that transformation so that only the part that changed is taken care of. So this very much sounds like what in the model transformation community calls incremental transformations, but incremental transformations also have an a priori scheduling. So what we did.
It sounds like a rewrite system.
It's also, of course, these are rewrite systems. Of course they are. So to be able to cope with these two challenges, what we decided is to look at how would a RETE network look like if I actually, to control the execution of my rules. So I'm not going to go too much in the details of why the RETE network is actually a good idea there. It's mostly in the paper. But basically is that you have, in a RETE network, you have alpha nodes, which represents the state you're currently in. And then the beta nodes represent what has changed, right? What is applicable. So for us, the way we're encoding it is that your alpha node will be all the elements that are present in the rules, okay, that may be affected, so either in the condition or in the effect. And the beta rules will be the actual rule, right, that can be triggered. So basically, if this has changed, if the focus has been on, then this will be enabled. This rule will be enabled. But the problem is that we don't want to have any rule applicable at any time. So the way you actually cluster the things is by layer. So you look at the layer of what can happen at the same, so when you're in one layer, you cannot do multiple things at the same time. You can do multiple things at the same time if you're across layers. So that's why we used orthogonal components in the state chart. And basically, we introduced this beta OR nodes. So you have beta AND nodes and beta OR nodes. Basically, just looking if there is any change in my layer, then I will tell the rule that something has changed. So that's an OR, a logical OR. And here it's a logical AND where I check if everything is still true. So as I said, I'm not going to go too much in the details here. But from this initial configuration, I can see what is true. So the light is off, the button is enabled, the light button is enabled, the play button is enabled, I'm allowed to focus on the canvas. So all the green things here are enabled. You propagate these to the beta OR nodes, and they are all three enabled, and that enables rules A, B, C, and E. So from there, you can apply one of these rules. Actually, you have to apply all these rules to make sure that you have all possible paths from any state, and that's the tricky part. So what we do is that we created transitions for each time we actually apply a rule. And the application of the rules, so the creation of a transition will create a new state if it's not something, if it's not a configuration I have already reached before. And the way we do that is we actually call that refinements of the state charts. For more information why it's refinements, I would refer you to that paper. And so the process goes on by basically, well, now I've applied rule C, so we see that what is enabled and what is disabled. And from there, I can say, well, OK, I'm going to reevaluate what is available. So I know that from state 1, 2, 3, I've been able to generate state 1, 4, 5. And then from here, what can I generate? Well, I can apply rules A, B, C, and E. So I create my transitions, et cetera, and that's how you create your state chart model at the end. Okay, and the process ends when you have your queue completed. So here I didn't say that, but when it's underlined, when the state is underlined here, the configuration of the state chart is underlined means that that's the current one I'm evaluating. These are the ones that are applicable, so that I will have to revisit, and this is the one I have completely visited from all possibilities. So the process ends when my queue is actually empty. Okay? So as you see, you cannot know in advance what rule has to be applied when. Okay, so that was the refinement process where we actually transformed this state chart. And from there, well, we actually serialize it to some concrete concrete platform, very specific platform. Let's say I want to deploy it on the web, okay, or with that. So I will make sure to change all my. So here, if I go back here, all the actions. Okay, all the actions here are very abstract. The events I receive are press, finish, etc. So what do they actually mean in the platform is defined here with this mapping of the events. And from there, I can compile my state chart to anything that I can transform it to anything that any tool that allows me to compile the state chart to running code. For example, SCCD or Yakindu or something like that. And so at the end, I end up with a graphical user interface with its API, and then the executable code that calls that API. So the end result is generating domain-specific editors with custom graphical user interfaces and interaction methods. So the code is, the whole thing is available on GitHub. I asked the student to send me to let me have demos. So here's for the game of life. You can just simply create your cells, and if I click back on it, it deletes it. So that's pretty simple. So this implements the rules I just showed you. That's very, very trivial. If we get to something a bit more complicated, for example, music sheets. So I don't have a MIDI keyboard, but we've mapped some keys of my keyboard to notes, so I can just enter the notes and do that. Okay. I can also say, well, I want what's the timing of the note. It will go on the line automatically. I can also set it in timed mode, so how long I press the key will select the actual time. So you see, I instantiate. These are all language elements that I instantiate depending on how I've interacted with that. And we've been also able to reproduce known behaviors, from Eclipse or Atom PM, where I can just click create, simple stuff. I can drag drop. Where it is? I can drag drop stuff. I can check the properties, for example, things like that, right? So pretty simple stuff. So for the evaluation, what we did is that we asked ourselves, can we mimic the interactions using existing domain-specific editors, which I just showed you, and does the generation of the editors scale with the complexity of the interactions of the rules? So we've looked at 3 big domains, let's say, something that is super simple, something that is medium, where you have to do drag and drop and enable, disable some buttons in the toolbar, and something that is completely new, where we mimicked flat.io. If some of you do music editing, staff editing, would know that's what we mimicked. So that's what we tried to do here as a proof of concept. And for the scalability, what we did is we took these models and we've synthesized, we've automatically generated example of interaction models using Monte Carlo simulations based on a fixed meta model of 10 classes, a fixed interface model with 10 layers, and interaction rules that are randomly generated with 60% overlap. Okay, which corresponds, so that why we chose these parameters is to be as close as possible to the three cases we had, okay, to be more representative. And from that, we ran a lot of experiments, and basically what we see is that the creation of the RETE structure of the RETE network is very, very quick. So even at 300 rules, it takes just less than 3 seconds. By the way, these The ones we actually did by hand were in the order of 4, 5, 40, 60, so nothing more than 100 rules, so it runs pretty quick. And for the refinement, so the time is here, the orange plot, so it's so the correlation showed us that it's actually quadratic, so it's pretty fast. And so is the memory footprint of that. Okay. You're probably going to ask me, why do you take as basis the number of rules? Because it may differ a lot. So given the setup that we did, the number of rules is correlated with the number of times you actually pass through the queue, okay, the queue size. So that's linear with respect to the number of the length of the queue. So that's the reason we plotted that. Okay, so there are numerous limitations of our approach because it's just a proof of concept, right? A first step to be able to actually do that, just being able to do that. What we've seen is that the number of rules can grow quite fast depending on the number of interactions you want to do. So it can get really, really hard for an actual designer, user experience designer to write, 100 rules and make sure that, what's the conflict between the rules, what's the overlap, the dependency between the rules and all that. It's a lot to manage at the same time. So we're working on, well, we actually have, that's a journal extension of it, of this paper. We're working on a coordination mechanism that allows you to reduce the number of rules by defining the equivalent of CTT operators, for those of you who may know that. So like a rule can trigger another rule or disable another rule explicitly and things like that. And we also have parameter passing between the rules, which make it faster. Also, our approach requires that you have built a library of possible interactions, right? And the Statechart, what it does is calls the right API. So it assumes your API is there. And we've only focused on graphical domain-specific editors for now. We're starting a user study in November on to measure the productivity for engineers to, we're doing a control experiment where we're going to give engineers to build the same editor, one using our approach and one not using our approach, and see which one is more productive, etc. So that's where we're at. Okay. So that's it for now. So if you have questions, please do. Thank you.
Plenty of time for questions.
I'm wondering if you could offer any preliminary comments on the user study. What are the challenges? How's it going?
Yeah, so we're actually running, we finished the protocol now and we're running it beginning of November. We've alpha tested it with some students in the lab, and it's pretty good actually. So the only thing is the interaction rules, I showed you, they look, I guess that should be a slide with some of them. Yeah, they look like this. Currently, we don't have that graphical user interface. It's mostly textual with an Xtext editor where you define the rules. So that may be a bit, changing a bit that. But otherwise, we're able to do quite a lot of things. We're able to deploy it on Arduino. So it's an Arduino that actually controls the editor, and you also get the output also on different mediums.
Talked about how you can generate these interactions directly from
rules.
Rules, and that gives you the set of interactions that can happen. But for many applications, I guess it's restricted which interactions can actually happen. So is there? I mean, not all events can happen at the same time. The layers restricted somewhat, but for some applications, I can imagine you'd want to have it even more restricted.
Yes. So the whole point here is that the same person who builds, the language or the UI or things like that, so like the language engineer, let's say, side, will build that. And so if you're building domain-specific editors, you're constraining stuff, right? So it's up to the engineer to define what he wants to what interactions he wants to constrain, and given that, then the user will only be able to use these interactions. So like if in my demo here, I wanted, I don't know, to type something here, it doesn't allow me, right? Right. So it's only the interactions that you have defined in your here that are allowed. Now that may bring. I have time. I can extend a bit. Okay. Okay. So that may bring some questions like, okay, but what happens if I have a lot of rules to do and I want to reuse the editor, right? So we do a lot of reuse of different languages, but what about these interactions? How can I reuse them? So our idea is to basically look at these state charts that are generated and allow to refine these. So I take an existing one, and then I want to say, well, the way you actually go from interact from here to here, I wanted to do more steps or different things. And so how can I refine that transition? So I can take state charts and refine them into more specific state charts and try to control that to be able to reuse interaction models, definitely.
More questions? So a follow-up question is, you talked about, your presentation was very nice in explaining how these state charts are generated. So how does the user actually specify how these constraints, how do they impose these constraints on the model? What are the kinds of rules that they write?
So they literally write that, but I don't have the meta model here. But basically, your interaction rule can contain has a condition and an effect, and the condition can have elements, and these elements can be essential actions, can be language element from the DSL, so they're all mapped. You refer to that, or they can be elements from the graphical user interface. So you could have interactions that are completely only the user interface, like clicking something and then a pop-up will open to give you the about or the help or something like that. And then you can have interactions that are completely language dependent. So yeah.
Okay. So thanks. We should thank the speaker.
Okay, thank you.